Exam next week, that is on 18th. That exam will cover all multiple choice questions, probably 20 or 25. I still have not written the exam, but no more than 25 questions. Those questions will come primarily from molecular orbital theory that we have talked about. It will come from point group classifications that we discussed, and also coordination complexes, isomerism, naming, and all that stuff. Is that clear to all of you? Okay, so that exam will be uh, due on November 18th. Today is 11th, right? So on 18th is the due date. You will have 120 minutes to complete the exam. Usually that exam is only for 60 minutes, but there are some people who would need a little bit more time. So I kind of gave extra time to everybody. So you will have about 2 hours. Once you start the exam, you have to finish that in one sitting. And you will see the grade right away as soon as you finish and submit your answers. All right. Are there any questions on this exam? So next week, we will not have a lecture. Next Wednesday, we will not have a lecture. So don't try to show up on the web. And by Monday, we might put some lectures on acid bases, all that stuff, but that will not be part of the exam. So as soon as the exam is finished, you should be preparing for that one. And then we'll also cover, for the interest of biochem majors, something about medicinal inorganic chemistry, which we will also post it. And of course, we'll also discuss in the class. And then there are a couple of other topics that would like to cover, that is on the descriptive chemistry of hydrogen. So that is about the time we'll have to finish this course. All right. So some aspects of descriptive chemistry, some on medicinal inorganic chemistry, some on the advanced concepts of acid bases. When I say advanced concepts of acid bases, I'm talking about superacids. I mean, you may be familiar with Lewis acids, Bronsted acids, or Arrhenius acids, but you may not be familiar with what we call superacids. Acids much stronger than either Lewis acids or Bronsted acids. And where does that extra acidity come from? So especially as chemists, if you're looking for a really, really strong acid, stronger than sulfuric acid, stronger than nitric acid, where would you go? So those are all the topics that we'll be discussing in the acid-base chemistry. Okay, thanks, Alyssa. All right, so before we continue, I just have to complete a couple of assignments. I think last week, as time was running out, we were talking about the 18 electron rule, right? And then we did some examples on how to calculate the total number of electrons in a coordination complex and be able to estimate its stability. So having 18 electrons is like an octet rule in simple covalent molecules. So when a molecule has 8 electrons around it, or the atoms in a molecule have 8 electrons around them, they kind of get some extra stability. That's what the Lewis theory was. Similarly, on the same lines, the coordination complexes too, we have 16 electron rules and 18 electron rules. So given these rules and the stability of these complexes, we have estimated, we have classified all the ligands into 2 electron ligands, which are neutral. We classified some as anionic 2 electron ligands. We classified some as anionic 4 electron ligands. And finally, we identified one of those anionic 6 electron ligands, which is cyclopentadienyl complex, right? And then using those examples, I think we kind of looked at some complexes and tried to calculate them. I think we did talk about the rhenium complex, right? Rhenium complex, that is an example that we were taken last time. And we also have done some on metal carbonyl complexes and identification of the metal based on the fact that it is an 18 electron rule. I think we did that too as an example in the last week. So before I continue, are there any questions so far on those topics? Anything that's not clear? I think I gave you a presentation also on the coordination complexes, but that is in addition to all that stuff we have covered in the live lectures. Anything that's not clear so far? Again, those of you who joined late into the lecture, we just made an announcement that next week, next Wednesday, there will be no class, but there will be an exam that will be due November 18th. Exam will be available starting about midnight of 17th or early morning of 18th. I don't know how this Canvas works, but definitely on 18th, you should be able to find some time slot and finish that. Okay, so you will have about 24 hours, which is plenty of time. The exam is pretty simple. It's all multiple choice. There are no tricks. The exam is straightforward. We'll give you a bunch of molecules and ask you which of these molecules will have, let's say, D4H symmetry, right? So you should be able to look at those things and be able to identify which molecule has. Sometimes I may give you a cluster of compounds and then ask you to identify those molecules that have, let's say, C2 axis of symmetry. So you should be able to look at all the molecules and be able to answer. So it's not a complex one. You should be able to finish that. As long as you understand what was going on in the lectures and the PowerPoints that I've given you, and also the lectures that I uploaded. Between all of that, I think you should be able to answer those questions. Any questions so far? Anything that's not clear? Because we just have 1 week time. All right, so maybe I'll start with a question that I'll ask. Let's say I have a complex. That is a charge. This complex, I tell you, obeys 18 electron rule. If that is the case, what should be the charge on this complex? What should be the value of Z? Can we quickly calculate and let know what the value of Z should be? You all can see the complex, right, on the board? Hmm? So how many electrons carbonyl donates to the complex? Remember, we went over this last week.
2.
2 electrons. So how many carbonyl groups we have here?
5.
5. So what is the total contribution of electrons from the ligands now?
10.
5 times 2 is 10. Right? So if this complex obeys 18 electron rule, then it is imperative that the cobalt should give 8 electrons, right? So which oxidation state of cobalt will have 8 electrons? Neutral, anionic, cationic? If it is cationic, what is the charge? If it is anionic, what is the charge? So to answer that question, you need to first write down the electronic configuration of cobalt, right? The neutral cobalt. So how many valence electrons neutral cobalt has? Hmm?
9.
It's 9 because cobalt is argon 3d74s2. That is where the electronic configurations come into the picture. That's the reason why we spent so much time early on. So by now, you should be able to tell very quickly what the total number of valence electrons. So cobalt has 9 electrons, but we only need 8 electrons from cobalt. So how many electrons should we knock it off from cobalt to make it 8?
1.
1 electron. So if you remove 1 electron, then this value of this should be +1. You see how wonderful we can do these things nicely? The 18 electron rule, how it helps to identify the charge on the complexes. Is this clear to all of you folks? Okay. Sometimes in exam, there'll be a question like this. We'll throw a complex and say this is 18 electron complex. So find the charge, or sometimes I'll ask you for the identity of the metal. Sometimes I'll give an unknown ligand and ask you to identify which of the following should be the ligand then. Because you have the classification, right? You have neutral 2 electron ligands, you have anionic 2 electron ligands, you have 4 electron anionic ligands and 6 electron anionic ligands. So you have a list of all those things. So based on that, you should be able to identify which of them should be the one. Yes, sir. Trevor, question?
I was gonna ask if you could just slide to the left a little bit. I'm sorry.
Oh, I'm sorry. Please, because I can't see myself, so please. I'll be more than happy to get away from the screen. You all understand the logic, right? Is that okay? Right. The next thing that we'd like to introduce to you is hard-soft concept. Remember when we were talking about the atomic properties, we did consider a little bit about what we called hard and soft atoms. Anyone remembers which atoms are generally hard and which are soft?
The one they have a smaller molecular weight, they are harder, and the larger ones are softer.
Wonderful, excellent. So here is the observation. By looking at variety of complexes, what people found was if your metal is soft, then a soft metal always goes with a ligand that is also soft. On the other hand, if you have a metal that is hard, it goes with an atom of a ligand which is hard. Let me give you an example. Let us say I have a ligand which is SCN minus. Anyone remembers what this is called? It's not cyanide. We have an additional sulfur atom in this. So we should call this as thiocyanate, right? It's a thiocyanate anion, SCN minus. When you look at this SCN minus, you have sulfur, which is large, and carbon and nitrogen, which are small. So this is a complex or a ligand that has both soft atoms and hard atoms. Now, the way this ligand binds to metals depends on the hardness and the softness of the metals. For example, if I were to have Hg plus ion and a titanium 3 plus ion. So the question then is, in SCN, I have 3 atoms, sulfur, carbon, and nitrogen. So if I were to bind this ligand to the complex, which is the mercury or titanium, which of these atoms in this functional group will attach to mercury? Is it going to be carbon, nitrogen, or sulfur? So to answer that question, we need to know whether mercury is soft or hard. If you look at the periodic table, where is mercury? Is it on the top of the periodic table or somewhere in the bottom?
Mercury is soft.
Mercury is very soft. So which of these atoms in this ligand, SCN, is soft?
Sulfur.
Sulfur. So when you make a complex between mercury and thiocyanate, it is the sulfur end of the thiocyanate that attacks the metal. On the other hand, if I were to bind the same thing with titanium, titanium is very small, highly charged compared to mercury, so it's a hard. So titanium will then bind with carbon end or nitrogen end, not with the sulfur. Because soft goes to soft and hard goes to hard.
Professor,
Yes.
is there a reason why hard goes with hard and soft goes with soft?
It is purely to the bond energies. See, when you are bringing electrons of mercury with the electrons of the sulfur, right? You need to have the electronic energy levels more or less similar. So when you talk about soft and soft, you're talking about electronic energies more or less similar. That's where the binding happens. That makes sense, Gurveer?
Yes, thank you.
Good. One of the important implications of this, if you extend this argument, we all know silver, right? Silver is a very soft ion because it's very big. And if you look at the periodic table, right, it is below copper, it is bigger than copper. And for that reason, it's very soft. But then silver being soft, and it is also considered as a great antimicrobial agent, right? Silver has a phenomenal wound healing ability, and it also cuts down bacteria. So olden days, when there were no antibiotics available, I'm talking about pre-1900s, silver was found by humans to have a phenomenal antibiotic activity. I think in the beginning, we also talked about the famous saying, you know, born with a silver spoon in the mouth. So rich people used to put a silver spoon in the baby's mouth so that there will be no infections, gum infections for the kids. Okay, so that's how popular silver was. But now we understand a little bit more. And one of the reasons why this does is in the bacteria, we have these disulfide bridges, right? For those of you who have been biochemistry, know this better than I do, that most of these bacterial proteins do have a sulfur-sulfur thiobridges, they call them. So when you bring silver in contact with the sulfur-sulfur bond, that silver removes the sulfur from these biological active molecules and deactivates them. So that's for that reason, silver, even today, is used in a lot of antimicrobial applications. Silver creams are used. You know, mostly chalcophilic elements. Chalcogens means sulfur. Oxygen, sulfur, selenium, tellurium group is called chalcogens. So for that reason, we call this chalcophilic. The philic means something that loves, and chalco means chalcogens, sulfur, selenium, tellurium. Okay. So it again makes a complex with the protein using the sulfur end of it, and then deactivates the function of these proteins. So there are a lot of implications, biological implications, and there is a big field called bioinorganic chemistry, how these metals bind to a lot of biologically active molecules. It's also used in ligation therapies. We'll get to that when we look at the medicinal applications of inorganic chemistry. So is this clear, folks? So which one binds to what, and which ligands bind with which type of metals? So it gives you, I mean, if you ask me, are there any exceptions? Of course, there are some exceptions, but this is a general rule. Just like chemistry can be frustrating sometimes because, you know, there's no hard and fast rules. but these are some of the general observations. So an educated guess is going to be if a ligand has sulfur, it generally binds with a soft metal, like lead, for example, is again a soft metal. So lead again binds with the sulfur end of this. So especially if you have organic molecules, for example, if I have furan type of rings, and then if you have a sulfur group right there, or SCH3 twice. So when you bring a metal, depending on the nature of the metal, either the oxygen or the sulfur will bind it with it. Okay. So this is a very interesting chemistry. Right now, the current understanding is because of the compatibility of the energy levels. So Gurveer. All right.
Professor, I was wondering, from after which metal do you consider the metal to be soft? Like, what size would you consider to be large?
I know that this question is going to come in. That's the reason why I told you there are no hard and fast rules. If you are comparing two metals, right, you can make an educated guess based on the size of the metal. Like, for example, if you are comparing a lithium with a complex of barium, for example. Okay. So then clearly barium is much softer compared to lithium. So if you ask me about lithium and sodium, it's not that soft compared to lithium as barium is. Okay. Good. So this is about what I would like you to know for the exam. All right, this is up to this point. Hardness, softness of the complexes, isomerism of the complexes, Fachner isomerism, linkage isomerism, hydrate isomerism, ionization isomerism, cis-trans isomerism, so much of stuff we talked about, right? Coordination complexes, all that is will be a part of the exam. Naming of the complexes, finding the charges, 18 electron rule. I think we covered quite a ground on this interesting inorganic molecules. So before we move to the next topic, are there any questions so far? Anything that's not making sense? So at this time, what I will do is then if you have any questions on all the topics that we have discussed so far, point group classification, symmetries, molecular orbital theory, coordination complexes. If you have anything, because your exam is next week, if you want, I can have a review session or some kind of an office hour session next Monday around the same time. Is that good for you? Do you have any other class going on Monday at 11 o'clock? How many of you cannot make a Monday 11 o'clock?
It would work for me.
Okay.
Same works for me.
It works.
Is there anyone that time doesn't work for you? I just would like to hear from any single person. So because Wednesday is the exam, right? At least between now and the weekend, and I'm sure you're going to study some. As you read more and more, I'm sure you'll have more and more questions. Because you're
Dr.
trying to,
Chari,
yes.
is it going to be the same format, like the 25 multiple choice, or is it going to be different?
No more than 25 questions.
Okay.
Okay. It'll be all multiple choice. There will be no write-in answers for this. And there will be no mix and match.
Is the final going to be cumulative, or is it going to just be like another exam?
No, final is going to be cumulative. Okay. I'm sure I think I wrote it in the syllabus for the final exam. So those of you who have not done well either in the exam 1 or 2, but you do well in the final exam, there will be considerations for bringing up your grade. Because final is cumulative. But I don't think this applies to this class because most of you have done really good in the first exam. And I'm absolutely confident that you will do very well in the second exam too.
Is the final going to be the same format as these two exams?
That's correct, yes. But final may have a little bit more questions, but I'm not sure. But it will be all multiple choice questions. It will not be repeat of exam 1 and 2, but there'll be different questions in the final, but the same topics.
I have a quick question.
Yes.
I was like experiencing computer glitches at the beginning of this class. So I didn't hear, you said that were we going to have 24 hours to start the exam in one sitting, or how was that?
Once you will have, I think November 17th, it is going to start showing up in your Canvas. The exam will be done, will be available. I think November 18th night, it will shut off. So you will have, I think, 48 hours.
Okay, then. Thank you.
And then once you start the exam, you can't stop and come back and do that again. I mean, you have to finish that in one sitting, and you will be getting about 120 minutes. You're allowed to keep a periodic table with you, and your notes, lecture notes, you can keep it with you. And you can also keep a point group classification chart that we developed, that you can keep that too. Whatever you're comfortable with. You can also, you know, it's almost like an open book exam because I cannot proctor it. All right. So let me see if you have any burning questions at this time, because I want you to use this time to study rather than listening to me. Anything that's not clear, anything that you want me to go over them one more time?
Professor Chari,
Yes.
so it starts with the information with the molecular orbital theory up to this point with this
Correct.
information today? Okay.
Yes. If you go back, I think there's a lot of material, right? Those of you who are taking the notes from every point we've been talking, we covered so much of ground in symmetry, classifications, you know, the sigma H, sigma V, sigma Ds, all that stuff. With lots of examples. I think we gave you several examples on how to classify the point groups.
I have a question, Dr.
Austin,
Chari.
yes. Mhm.
So you gave a lot of the examples of the elements on the periodic table that like have different names for their
Mhm.
atomic symbol. Could you
Right.
give the ones for tin and antimony?
Antimony is stibium, and tin is stannum.
Could you write those down?
Yeah, sure.
Thanks.
Tin is stannum, and antimony is stibium.
Thank you.
But modern inorganic chemists don't really follow for, you know, like antimony, they don't write stibinate, but they will say, you know, if it is tin, right? They don't use tin, stannum, they will still use it. But if it is a cationic complex, they sometimes say tin. But that is not that is not legal. But people, don't be surprised in the journals if you see those small deviations from the rules here. But in the textbooks, when we write, we use these things. But again, you will have a periodic table with the full names, right, of the things. You should be able to get one in the internet that will have all the names. Like gold is aurum, right? AURUM. That's the reason why the symbol is AU. So whenever you see a symbol that sounds different than the colloquial name of the element, then you know that it's going to be having a Latin origin. Then we went over some of them, right? Tungsten, for example, we write W, it's a wolfram. Copper is cuprum. But others are okay, like manganese, nickel, cobalt. Right. Iron is ferrum, so that's going to be slightly different there. Ferrate, we don't say ironate. Thanks for asking, Austin. Okay, other things? So in fact, you will have a lot of wealth of information available on the internet in terms of naming of coordination complexes. You must have lots of lectures by others too. So if you, they'll be using different examples. So if that's comfortable with you, you can watch them too. It's not like what it was 30 years ago, where the students had access only to the professor and the textbook. Today, the entire world is open to you. So it makes a big difference. And thing is, of course, you need to find time to sit down and watch those. All right, if there are no other questions, then we'll meet next Monday again at 11 o'clock and then cover any questions you may have before we take the exam. Is that okay with all of you? Yeah? So we'll have an additional instructional time on Monday, 11 o'clock. I will not be teaching anything new, but I will try to answer any questions you may have that may be coming up because you are going to spend some time between now and Monday. Okay. All right. Happy reading, and we'll see you next Monday at 11. Thank you,
Professor.
Thank you.
Thank you,
Have a good
Jari.
day.
Thank you very much.
You.